Let us discuss this second isomorphism theorem on groups. The statement is like this: if H and K are normal subgroup of G such that H is a subset of K, then in that case G by K is isomorphic to G by H upon K by H. The second isomorphism theorem will be the application of first isomorphism theorem. You will see that at the end for that one. But now here let us see that given H is a normal subgroup of G and H is a subset of K. So by the previous theorem that I have already discussed with you, it implies that H also will be a normal subgroup of K. Now, so K by H can, so therefore the quotient group K by H can be formed, because if you remember that the quotient group can be formed, say G by H, if H is only a normal subgroup of G. So here also, as H is normal in K, so it implies that K by H also can be formed. Again, by the given condition, H is normal in G, so it means that G by H also can be formed. Similarly, K is a normal subgroup of G, so the quotient group G by K also can be formed. Now let us recall this one. We have I've discussed with you this one, that if these statements are satisfied, that is this one: if H and K are normal subgroup of G such that H is a subset of K, then K by H, the quotient group K by H will be a normal subgroup of G by H. So we need this result also. So for this one, what I need to prove now is that G by K is isomorphic to G by H upon K by H. So that means there exists a mapping FC from this one G by H to G by K such that that mapping is homomorphism. It is on 2. It is on 2. So if you can prove those two conditions for F, then we can apply the first isomorphism theorem. Now here, let us define the mapping F from G by K to G by H to G by K by the rule F of Hx is equal to Kx, because what are the elements of Hx? G by H, it is of the form HA such that A belong to G. So F of Hx will be Kx. Here again G by K contained element of the form Kx such that X belong to G, where X is in G. So we define it as F of Hx is equal to Kx. F is well defined. So for this one, let us suppose Hx is equal to Hy. And this will imply that Hx y inverse is equal to H. By multiplying on both sides but on the right by y inverse, then you'll get Hx y inverse is equal to H. And this will imply that xy inverse will belong to ky, because H is a subset of K. If xy, from here it will imply that xy inverse belong to H, but H is a subset of K, it will imply that xy inverse will belong to K also. So which means that kxy inverse is equal to K. This is by the theorem on a subgroup of a group. If xy inverse belong to the subgroup, then in that case kxy inverse will be equal to K, which means that kx will be equal to ky. So this, what is kx by definition of F? It is F of Hx is equal to F of Hy. So this implies that F is well defined. Now number 2, F is a homomorphism. Let Hx, Hy belong to G by H. Then what is F of Hx, Hy? This is equal to, it will be F of Hxy, because Xh is same as Hx, as H is a normal subgroup of G. So that's why Hx into Hy is same as Hxy. And by definition, what is F of Hx? It is Kx. So here in place of X, it is K. So it will be Kxy. And again, K is a normal subgroup. So you can write this one as Kkxy. And this will implies that Kx is equal to, is equal to, this will be equal to Kx into Ky. But what is Kx? It is F of Hx. And what is Ky? It is F of Hy. So this means that F of Hx, Hy is same as F of Hx into F of Hy. So this implies that F is a homomorphism. So we are done with the first condition of the first isomorphism theorem. Now let us prove that F is on 2. Now how to prove that F is on 2? Given any Kx belong to G by K, we need to show that there must exist a pre-image of this Kx in G by H. So given any kx belong to G by K, it implies that this x is an element of G, which implies that if x is an element of G, implies that hx will belong to G by H by the definition of the quotient group. So this implies that kx now is equal to f of hx. That means for every kx belongs to G by K, you can always find an hx belongs to G by H such that kx can be expressed as f of hx. So which means that f is on 2. Now let us find, now since you can see from here that f is a homomorphism or an onto homomorphism defined from G by H to G by K. Then by the first isomorphism theorem, if a mapping defined from one group to another group is onto an homomorphism, then in that case, that group G by H by kernel of f should be isomorphic to G by K. So now here what we can have from this one, since f is onto and f is homomorphism, so G by H, the quotient group G by H upon kernel of f must be isomorphic to G by K. So we are able to show up to this step, okay? But now I need to show that kernel of f is equal to this one. Kernel of f is equal to K by H. So how to prove that one? So let us find out kernel of f. Kernel of f by definition, since it is a mapping defined from, you can see from here, it is a mapping defined from G by H to G by K. So kernel of f will contain those elements hx such that f of hx belong to G by H such that f of hx is equal to K, the identity in G by K. So if I can prove that kernel of f is equal to K by H, then in that case we can substitute it here. So for this one, let us take an element of hx belong to kernel of f. So kernel of hx belong to kernel of f, by definition it will imply that f of hx must be equal to K. Now what is f of hx? By the definition that we define on f, it is kx. So kx is equal to K. And this implies that x belong to K. Now if x belong to K, it implies that hx will belong to K by H, the quotient group K by H. Because what is the definition of K by H? It is that ky such that y belong to K. So here x belong to K, it implies that hx, it is hx only. Made mistake here. It should be, this one should be H. So hx should belong to K by H. So hx belong to kernel of f implies that hx also belong to K by H, which means that kernel of f is a subset of K by H. Now next, let us show that any element of K by H, take hx belong to K by H, and we need to show that this hx belong to kernel of f. So if hx belong to K by H, by definition of quotient group, it implies that this x should be an element of K. And from here it will implies that kx, if x belong to K, implies that kx is equal to K. And what is kx? It is f of hx, this is equal to K. Now since the mapping of this element hx under f is equal to K, the identity in G by K or in K by H, so this implies that hx belongs to kernel of f. That is K by H now will be a subset of kernel of f, because every element of K by H also belong to kernel of f. So from this one star and this double star, we can conclude that kernel of f is equal to K by H. Therefore you can substitute it here by the first isomorphism theorem. G by H upon kernel of f. Kernel of f is this one, K by H is isomorphic to G by K. So this is the proof of the second isomorphism theorem. Hope it is clear. In case if it is not clear, you please let me know.